Alrighty, this is section 8.3, Math 1149, and we are talking about solving trig equations. And in this first part, we're going to just cover some basic equations, and then after that, we'll get into how to solve some different categories of trig equations. So here we have the sine of theta equals 1/2. Now think about that. It's very similar to an algebra equation in that, if you have 2x minus 13 equals 7, well then what you're looking for to solve that is you're trying to find out what value or values could x be such that this would be a true statement. That's exactly what we're doing with a trig equation, except for the variable is theta. Sometimes it's x, but here it's theta. We want to know what are the different values could theta have so that the sine of theta is 1/2. And so, and in this first few examples here, we're going to, excuse me, what we're going to do is we're going to come up with a general solution, a way to write all possible solutions for this. So let's take our unit circle here and take a look around and see if we can find some angles that have a sine value of 1/2. Remember, the sine is the y-coordinate. So here's at pi over 6, that's 1. So 30 degrees. And then we have also another one over here at 150, or 5 pi over 6. Now that's it for if we're only looking from 0 to 360 degrees. There's two angles. However, if you think about it, there are actually infinitely many angles that have a sine value of 1/2. If we don't restrict ourselves to just the first 360 degrees, if we remember, all coterminal angles have the same trig function values. So, for example, at 30 degrees, here at 30 degrees, if I have an angle that has the same terminal side of that but goes around one more full rotation. So, example, if I'm at 30 and I go around in a positive direction, another 360 degrees. So 30 plus 360, because the 360 is one full rotation, no matter where you're at. So 30 plus 360 is 390. So 390 degree angle also has a sine value of 1/2. And that stands for all angles then that have the same terminal side as a 30 degree angle. Same goes for 150 degrees, since its sine is 1/2. If I added 360 to that, whatever 150 plus 360 is, that angle will also have the same sine value. So you can see I could keep going around in a positive direction, or even go backwards in a negative direction and subtract off 360 degrees, or if I'm in radians, I'd subtract off 2 pi, and I would come up with literally infinitely many angles that have the same sine value. So when we're being asked to give a general solution, and that would have to be listed in the problem statement, find a general solution. If we're being asked to find a general solution, which means find a way to describe all possible angles, then what you're going to do is you're going to say, kind of write something like this. It would be theta is equal to, and if we were in degrees, it would be 30 degrees plus 360 degrees k. I'll explain the k in a minute. And then, of course, we also had theta was 150 degrees plus 360 degrees k. Now that k, so we're going to say where k is any integer. So if k was 1, remember integers are the positive and negative whole numbers plus 0. So K could be 1, 2, 3, 4, or -4, -3, -2, -1, and so on, and including 0. So if K is 0, then we're just talking 30 degrees and 150 degrees. But if K is 1, then it would be 30 plus 360 times 1, or also 150 degrees plus 360 degrees times 1, and so on. So allowing to have this K here and adding on multiples of 360 covers all the angles. Now, if this happened to be, if we wanted our answer in radians, then here's how you would give your answer. Theta equals pi over 6, because that's the radian equivalent. And since we're in radians, we would come back around 2 pi k. So we're going to add on multiples of 2 pi instead of multiples of 360. Again, k is any integer here. And then for the 150, that's 5 pi over 6 plus 2 pi k, where k is any integer. Okay? So that's an example of how to write out all possible solutions for theta when the sine of theta equals 1/2. All right, so here's another couple problems. One is the cosine of theta is negative radical 3 over 2. Let's give our answer in radians this time. So we're looking for theta such that cosine theta is negative radical 3 over 2. And if you look here, if we're looking for the cosine, that would be the x-coordinate. And so over here at 5 pi over 6 has a negative radical 3 over 2, as well as 7 pi over 6 also has a negative radical 3 over 2 for the cosine. And so those would be our two solutions that we would start with, and then we could just add on multiples of 2 pi to that to come up with all solutions. So again, these first few examples we're going to do general solutions. A way to write out all possible solutions. So it'd be 5 pi over 6 plus 2 pi k, and theta is equal to 7 pi over 6 plus 2 pi k, where k is any integer. All right, let's look at the tangent of theta equals 1. All right, now let's see. Let's take a look at here where the tangent is 1. Okay, so here we go. Tangent of theta equal to 1. Well, that would be, again, the sine divided by cosine if we're going to look at these unit circle coordinates. That's how we come up with the tangent, is sine divided by cosine. So y divided by x. And if we're looking for 1, y divided by x would be pi over 4, right? As well as, down here in the third quadrant, look, we have a negative radical 2 over 2 divided by a negative radical 2 over 2. So that's a positive 1 also. So you have pi over 4 up here, and then you have 5 pi over 4 there. Now, the one thing about the tangent, though, is that the tangent values repeat more frequently than the sines and cosines. So all we have to do is take that very first angle and then add multiples of pi, which that's the pi is the period for the tangent. And so see what happens when we do that, and I think you'll see what I mean here. So if we let theta equals pi over 4, which was the first angle we come to in going around the unit circle, and add to that its period, pi times k, where k is any integer. Okay. So if you think about it, if I add pi k to that, like let's just add pi, just the first iteration when k is 1. If we take pi over 4 and you add pi to that, I have to have a fraction to add another fraction. So it'd be pi over 4, and then this would be plus 4 pi over 4. So that is 5 pi over 4. You see, if I just, since tangent, and actually the same would be for the cotangent, since tangent and cotangent repeat more frequently than sine and cosine, you're going to have, you're going to duplicate things here if we try to keep going by increments of 2 pi. So what we're going to do is, so if we pick up this, the very first angle you come to, going around the unit circle, which is pi over 4, that is a solution. And then not do the 5 pi over 4 here, but just simply add on multiples of its period. Then we'll pick up that 5 pi over 4. Okay, we'll do one more here where we're going to do a general solution. Find a general solution for all angles. So here we're going to say, find a general solution. Okay, so now don't let this fool you that there is a multiple angle in here. It's cosine of 2 times theta. That's cosine of 2 theta, which means cosine of 2 times whatever theta is equal to negative 1/2. So just imagine, I can't do this here since I'm recording, but imagine you just put your hand over that 2 theta. And this is the cosine, and just say to yourself, the cosine of some angle, the cosine of some angle is equal to negative 1/2. And so let's go find out, what angles have a cosine of negative 1/2. And since it's something that has a period, cosine has a period of 2 pi, we're going to look through the entire 2 pi here, not just the first pi radians like we did with tangent or cotangent. So we're looking, where's the cosine negative 1/2? Okay, so so you got up here 2 pi over 3, there's cosine 2 pi over 3, and then also at 4 pi over 3 down here in the third quadrant, it has a cosine of negative 1/2. So those are our 2 angles just going around in examining the first 360 degrees. And so what I could do here is just simply say, okay, we got, now remember, it's not theta that equals those angles. It's actually this, whatever this is in here, equals those angles. 2 theta is equal to 2 pi over 3 plus, and since it's a cosine, it's a period of 2 pi, so 2 pi k. And then the other angle that twice theta has a cosine value of was 4 pi over 3. Plus 2 pi k. Now remember, to find a solution here means we're trying to find out what theta is, right? We're trying to solve for theta. Now we have solved for 2 theta. So we're going to have to divide everything by 2. All terms need to be divided by 2 to solve for theta. 2's cancel here, give me theta. This would be 2 pi over 6. 2's cancel here, give me pi k. Same thing's going on over here. Theta, 4 pi over 6. Plus, and then our 2's cancel and pi k. We have a little bit more simplifying to do because 2 pi over 6 and 4 pi over 6 simplify. So this would be theta equals pi over 3 plus pi k. And this would be 2 pi over 3 plus pi k, where k is any integer. Right, so this right here would be our answer. Okay. All right, so that gets us started on trig equations, and then the next video will show you how to do some more different types of trig function equations.